in probability and statistics as an undergraduate. Oh, it's an amazing number. Okay, you guys can leave the room now. You already know this. The rest of you, I will tell you what you need to know here. So, okay, why is it called Monte Carlo? During the Second World War, they developed the technique because they wanted to simulate how neutrons bounced around inside uranium and plutonium cores in atomic bombs. Okay, so obviously it's highly classified, but since the technique is based on probabilities, and that's what gambling is all about, is probabilities, they called it the Monte Carlo technique for the casino in Monte Carlo. And I'm not too old to have fantasies, at least, so incidentally, there's a roulette room in Monte Carlo where the minimum bet is $10,000 just to get a spot at the table. And so every time you roll the wheel, it's another 10K. Well, I thought, well, maybe I'll take a stack of Hydrolyte CDs, which sell for 10K, but it didn't work. So anyway, they wanted real euros. Okay, so when would you use a Monte Carlo code instead of Hydrolyte? Well, basically Hydrolyte is a one-dimensional model. Things can vary with depth, but not horizontally. So anytime you have something like a sloping bottom, you have to use Monte Carlo, which can handle three-dimensional problems. You know, here the depth is different than the depth over here, so you can't run Hydrolyte. Or if it's a patchy bottom, this is seagrass, this is sand, you can't run Hydrolyte. Its bottom is all the same. I've had several papers published in the last couple of years where we were interested in computing light fields onto coral wall reefs. Wall reefs, a lot of times you'll have in the Bahamas or a place like that, you'll have fairly shallow water, and then it very quickly drops off to either a very steep or almost vertical wall, and you have corals growing on that. Those corals are at different depths. They have different light environments. You get different species of coral than you would growing up on the flat areas where you go snorkeling. So anyway, I put together a Monte Carlo code that can simulate the top of the coral, a sloping section, and the vertical wall part. And then you can put your sensor wherever you want it, point it in whichever direction. What we're going to work with this afternoon is a watered down version of this where there's a top and then a vertical part. I just took out the sloping part to simplify your efforts, but that's a 3D geometry when this coral here is going to affect the light field in the regions of the water out here. It's not a 1D geometry. If you have an object in the water, you want to simulate, you know, can I see this object, or what does this object do to the light field? That's a 3D problem. If you want to simulate ship shadow effects, that's a 3D problem. So the bottom line is anytime you have a 3D situation, you almost always use Hydrolyte. And the way you almost always use Monte Carlo. So what the deal is with Monte Carlo simulations, the essence of it is that you're going to use probability theory and random numbers to simulate a physical process. So what you say is, well, you know, I've got this light ray propagating through the water, and there's some chance it's going to hit a particle, and when it does, it'll scatter off in this direction or that direction, or it'll be absorbed, and then it will fluoresce, whatever it is. Those are all independent occurrences. And if the particle's scattered, then it goes over, hits another particle, scatters again, and so on. So you basically take the probability of occurrence of each separate event in a sequence. So the probability it'll be absorbed or scattered. If it's scattered, what's the scattering angle? If it's absorbed, does it stay absorbed or does it fluoresce? So you try to come up with what are the probabilities of each one of those occurrences, and then you use a random number generator to decide which thing is going to happen at each step of the way. So in the optics setting, the known probabilities are things like that a light ray will go a certain distance, that it'll be scattered. If it's scattered through a certain angle, if it reflects off the surface, what direction does it reflect off, and so forth. And then you trace millions and millions of rays and you build up a solution to the radiative transfer equation, one ray or one photon in the old terminology at a time. So you do a million simulations here, and each one will contribute a little bit to LU or ED, whatever it is. You average all those results together and you get a statistical estimate of the thing that you're interested in, like irradiance or irradiance. Okay, so the basic idea is you need to sit down and think about what's going on in Mother Nature, and then figure out how am I going to mimic that in a computer code. Okay, so what we'll talk about this morning then is what's a probability distribution function and what's a cumulative distribution function, a little bit about random number generators, a little bit about how you use these cumulative distribution functions to randomly determine distances and scattering angles and so on. We'll learn a little bit about Monte Carlo noise, statistical noise, and you'll do more of that in the lab this afternoon. And of course, there's the usual web book pages and such when you really want to dig into this. Okay, so basic probability distribution function. Well, what's that mean? A PDF is some non-negative function, I'll just call it P of X, such that the probability of X is between X and X plus DX is P of X dx. That's just the definition. So here, for example, if I write, say, the probability, if this is X is the height of adult humans in meters, then I can have a PDF of X that might look like this. So no adult is less than maybe half a meter tall, no adults more than 3 meters tall, but in between there's some distribution. Then, you know, on average, people are about 2 meters tall, plus or minus, you know, that much. So one of the things about a PDF is if you integrate it over all the values of its variable, it has to equal 1. That is, the probability is 1 that a person will have some height between 0 and being infinitely tall. So any PDF has to satisfy an equation like this. Now, if this were the PDF for scattering angle, it might be from 0 to 180 degrees, but that's the general idea. If you have the PDF, and let's say the one for human height, and you want to know, well, how many people are between 1 meter and 1.3 meters high, then you just integrate from 1 to 1.3, and that's going to give you the fraction of people that are that height. And if you integrate over the whole thing, you get the fraction as 1, that people have one height or another. The other thing to notice here is that whatever the variable X is, the PDF is a non-negative, or sorry, whatever X is, the PDF has to have units of 1 over X. So if X is meters, then this is the probability per meter of height that you'll have whatever height it is. Because that integral always has to equal a non-dimensional integral of 1. Okay, now the cumulative distribution function simply says, take the PDF and integrate from 0 up to some value X, and that's the CDF of X. So the cumulative distribution function, it's a non-negative function that tells you the probability that a variable has a value less than or equal to X. Okay, so you take the PDF here, you start integrating it, the CDF builds up, and it eventually goes to a limit of 1 because the integral under the orange curve here is 1. And so this is telling you that if you go to X equals 4 meters, the probability that the person is less than 4 meters high is 100% guaranteed. If you're at half a meter, CDF is 0. There's no chance that a human adult is less than half a meter tall. And if you're at 1.5 meters and you come up and you look across and that's maybe 0.8, then there's an 80% chance that the human out of the whole population has a height of less than 1.5 meters, would be 0.8 or 80%. Okay, so those are kind of the two main tools that you have to work with in Monte Carlo theory. So then you're going to use those CDFs and stuff along with the random number generator to determine randomly what happens at each step of the process along the way. So usually what gets used there is what's called a uniform 0-1 random number generator. That's anything, usually a computer program, but you could just, well, flip a coin. It simply means that the probability when you draw a random number, it's equally likely to be any value between 0 and 1. So the PDF for a uniform random number generator, it's 0 for the value of the random number less than 1. It's 1 between 0 and 1. So there's equal a chance that it'll have any value there. And then greater than 1, it's 0. There's no chance it'll put out a value of 1.5. So that's all it looks like. And every computer language in the world and Excel and all of those things, they all have some uniform random number generator. They'll also have ones that generate Gaussian random numbers and so forth. But bottom line is they're all doing really uniform random number generators. So here I just used one. I generated a long string, actually 1 million random numbers. I bin them into bins that are 0.01 wide, and I have 100 bins then. And I just counted up in this long sequence of 1 million random numbers, how many are between 0 and 0.01, 0.01 and 0.02, and 0.99 up to 1. And I would expect about 1% to be in each one of those bins, and pretty close, that's what I got. You know, there's a little bit of statistical noise, but there's my random number generator. Now, random numbers can be a little weird. So I have this computer program and it says it generates random numbers. So great, I start running it, it just generates one digit at a time, 1, 3, 5, whatever. So I have two strings of random numbers or digits that were generated by the computer program. And then I have another computer program and it says it generates random digits, equally likely to be a 0, 1, a 2, up through a 9. And so I run it and it generates a string of random numbers. So this one starts out, you know, generates a 4 and then a 5 and then a 2 and then an 8. This one generated a 1, a 4, and a 2, you know, an 8, 8, and and then a 3, 3, 3, 3, 3, and a 9, 6, and a 0, 0, and a 7, 7, 7, and so on. So you look at those strings of numbers. Which one of those do you think is not generating random numbers? Ben must know the answer. Nick, he's way. The top or the bottom here? The top? Yeah, why? Doesn't it look kind of suspicious that a random number generator would put out 5 3s in a row? Does that look kind of weird?
The first one looks like it's the previous number. Sure.
Yeah, it's actually, this is the one that was generated by the random number generator. This guy, it's not really random. This is a generator that says, generate a random number or a random digit, but if it's equal to the one that I just had before, throw it out. Never generate the same digit twice in a row. So you look at this and maybe you look at like 1 million of these and you never get 2 of the same number in a row. That's not a random number generator. And this one, you know, there's a 10% chance that it'll pick a 3. Okay, fine. Then it generates the next number completely independent of the first one. There's a 10% chance it'll generate a number a second 3. So there's actually a 1% chance it'll generate 2 3s in a row. There's 1 in 1,000 chance it'll generate 3 3s in a row. But that's perfectly fine. If you generate, you know, 1 billion random numbers, I guarantee you, you'll see strings of 5 3s in a row. And those are called runs. And so it's a run of here of 2 8s, a run of 5 3s, a run of 2 zeros, a run of 3 7s. And this is what leads to what's called the gambler's fallacy. So some yo-yo goes to Vegas with all his money. He's sitting at the crap table, he's rolling a dice, and it comes up, you know, 7 or whatever the good number is. And he rolls them again, and it's 7. Wow, he rolls it again, 7. Oh man, I'm hot, you know. I got a streak going here. I put all my money on the crap table, roll the dice again, boom, he loses it all. There's nothing whatsoever that when you roll 3 7s in a row at the crap table, that's just pure random chance. And so people don't understand that. So they think there's something mystical going on. And if I've rolled 5 3s in a row, I'm probably going to roll another 3. No, sorry, not the way it works.
There's a great
Here's another one, random arrangements of dots. So maybe you're flying over in an airplane and you're looking at bushes growing in the desert. Now, which blob of the dots here is the one that's where the dots are randomly arranged? Yeah, the one on the right, because now and then a couple are close together, now and then there's one long ways away. These guys here are practicing social distancing. None of them are very far apart. None of them get too close together. So there's a lot of statistical tests where people that study something like are in this species of plants, does it stake out its own territory and keep other plants away, or does it not care? And so you fly over, you get a map of where all the bushes are growing, and then there's statistical tests where you can like pick a dot, find its nearest neighbor, find its nearest neighbor, find the nearest neighbor, and then look at the distribution of the distances between those dots and do a statistical test to say, does this distribution look random? In this case, there's going to be an awful lot of dots with just about the same distance between them. Over here, you're going to get a broader distribution where some dots are close together, some are far apart, and that's the real random number, random arrangement of things there. Okay, so we're going to use, when we traced our light, this concept of a light ray, which is just this hypothetical construction that indicates the direction of propagation of light, and it usually has a weight with it, which will be in units of power or something like that, or energy. So this idea of tracing light rays, that's used in all like camera lens design, where you just follow this ray through the lens system and doing all the little reflection and refraction calculations and so forth. In that case, that's not a random number, not a Monte Carlo thing. They're just tracing where the rays go, but it's an example of using light rays. And light rays are sort of inherently a construction from geometric optics. You know, you don't have all the little things like diffraction and stuff included there. You're just doing kind of freshman physics optics. Okay. So now we need to figure out if we're going to randomly determine how far a light ray goes before it interacts. So we have to come up with some PDF for the distance the light ray is going to go, and then figure out how to use that PDF to determine how far the light ray will go. Well, you recall Beer's law here for a collimated beam of light, homogeneous dark ocean, et cetera. It just says the radiance in some direction decays as the initial value and e to the minus beam c times r, or if we use a non-dimensional optical depth tau, it's just equal to CR. So there's Beer's law, exponential decay of radiance or irradiance with distance. So now if you contemplate this long enough, you'll think, well, maybe the PDF for that happening is just an e to the minus tau. So the probability that the ray will be between distance tau and tau plus d tau would just be e to the minus tau dr, or that the probability distribution function is e to the minus tau. And you play around with that long enough and program it up and do some simulations as we'll do in the lab. And you'll say, yeah, I think that's the right PDF that would describe the exponential decay of light with distance. So now we want to use this and a uniform random number to randomly determine, in this particular case, how far does the light ray go. So you can think of that as kind of a change of variables, where I'm going to take that the probability of the random number between some value r and r plus dr, well, that's a uniform distribution. And I want that probability to be the same as the probability that the light ray goes a distance tau to tau plus d tau. So once again, you just have to contemplate this long enough to convince yourself that that's the way I should describe things. So if I integrate this from 0 up to r, corresponding to 0 up to distance tau, well, the u of r is just 1 between 0 and 1. And so that just becomes a 1 in dr and integrated. That just becomes r. And this thing right here is just by definition the cumulative distribution function. So if you integrate the e to the minus tau d tau from 0 to tau, that's just 1 minus e to the minus tau. Okay, so what we've ended up with is we're going to draw a random number generator and we're going to solve this equation for tau. And that's going to tell me what distance corresponds to this random number. So there's our equation. We solve that. And that gives me tau is minus the log of 1 minus r. But since r is uniformly distributed between 0 and 1, probabilistically speaking, 1 minus r has the same distribution as r. So I don't really have to do the subtraction. So I'll just say that when I draw a random number r, that tau will be minus the log of r. Notice r is less than 1, so the log is negative, so the distance is positive. So I'm just going to use this simple little equation with a random number to get the distance the light ray will go. Or if I want it in meters, just remember tau is equal to CR, so I can get the distance in meters. Okay, so then what we've done back here is we ended up with an equation. It was R equals to the CDF, and we solve for the variable. That holds true in general. You always want to come up with the CDF for your process, set it equal to the random number R, and then solve this equation for your variable, whatever that happens to be. So in other words, what you're doing is saying, I have the CDF for my process, which I had to go in my room, lock the door, and think about it till I figured out what that was. And then I have the CDF. Then I draw an R that's between 0 and 1, and I come over, and there's the value X. I'm solving this equation for X. So that's the general procedure. And then you just repeat this process time and time again to get new distances randomly determined. Okay, now there's a thing called the mean free path, which is the average distance that the light rays are going in your medium, water, whatever it happens to be. So we know the PDF is e to the minus tau. The average distance tau, well, the way that works is you take the tau that you're interested in computing its average times the PDF and integrate over all the values. That's simply how averages are computed, or mean values are computed in probability theory. And so you plug in the PDF for distance here, do the integration, and that turns out to be 1. one optical distance. And if you want to compute the variance, then you take the variable minus its average squared times the PDF, integrate. There's the equation, do the calculus. It also turns out to be 1. So when you have an exponential decay of light with distance, it's going to go some distance, tau, whatever it happens to be, and the average distance it goes is 1 optical depth. And so the variance or the standard deviation about that distance is also 1. It's very peculiar. So that's kind of telling you, you're getting a really big spread of values here. You know, some of these light rays are going to go 10 centimeters and some a meter, some 20 meters, but there's a chance for any of those. And there's a lot of variance, a lot of standard deviation. And if you remember that the tau is 1 over beam C, another way to say this is that the mean distance of light travels is 1 over beam C, and that the standard deviation of that distance is also 1 over beam C. So just
But remember, because this is not a normal distribution, that means 68%
right.
of the path are within 1 over C, right?
Yeah. Okay, so let's say we need to determine scattering angles. Well, here's our little geometry. You know, the light ray is initially going in the Z direction, C prime, I call it. It interacts with the particle here. It scatters off in some polar direction, psi, and some azimuthal direction, chi. So polar and azimuthal scattering angles. Now, remember the phase function, when you integrate over all solid angle, equals 1. Well, that, and this guy's always positive, so that qualifies that the scattering phase function is really a PDF for the particle scattering through angle psi and chi here. And we normally assume that its process is azimuthally symmetric. And all solid angle, there's our element of solid angle, and we're going to integrate over all 4 pi steradians. So we take this and say, well, okay, this is telling me how it goes from an initial psi prime psi direction into a final psi prime psi. I'd like to come up with a PDF for the psi part and a PDF for the azimuthal chi part. So how do we do that? Well, think of this guy here as being a PDF for psi times a PDF for chi. And the standard notation in probability theory is that you let a capital letter sort of label what the variable is, and you let the lowercase letter represent a value of that variable. So capital psi is scattering angle, lower psi might be 45 degrees. Okay, so for any azimuthal angle, it's equally likely that you'll get any chi value between 0 and 2 pi. So we can think of, well, the probability distribution for chi is just 1 over 2 pi. It's equally likely to have any of those values. And then the CDF, just integrate this from 0 up to chi. And so then we draw our random number, we solve for chi, it's just 2 pi times r. R going from 0 to 1 means the azimuthal scattering angle goes from 0 to 2 pi with any value. Then what's left over here, if we realize that the probability for chi is just 1 over 2 pi, is we plug that in here, and the P of psi part is just 2 pi times the scattering phase function times sine of psi. So now we need to, and of course, this guy integrates to 1. We learned that long ago. So now what we do to determine the scattering angle, the polar scattering angle, is we draw a random number r, we integrate the PDF from 0 up to some angle psi, and then we're going to solve this equation for psi given the random number r. Now, normally I'll have to do that numerically, but that's the conceptual process. Now, if we pick the beta tilde to be 1 over 4 pi, that's isotropic scattering, well, then the steps would go like this. You have a PDF, it's isotropic scattering. That means equal scattering into any solid angle. You convince yourself that beta tilde is really 1/4 pi. Plug that in here, do the integration. There's R, that integrates into this. You solve for the psi. And so it tells you that psi is equal to the inverse cosine of 1 minus 2R. Well, that looks pretty weird because you want the light going equally in all directions. Why wouldn't that mean that I pull, like I pick the angle psi to be anything between 0 and 180 degrees with equal probability? We pick the azimuthal angle to be any angle between 0 and 2 pi with equal probability, but that's not what we're getting here. Well, here's the proof. Here's what's going on. I plotted here 10,000 points on the surface of a sphere. So there's the North Pole. And I used an equally likely, or for the psi value, I picked it as being equally likely to have any angle between 0 and 180 degrees. And phi equally likely anywhere around here. Plotted the points, and you notice there's this collection of points near the North Pole. Well, and there's not as many at the equator. You look at that and you say, well, that doesn't look like a random distribution of points on the surface of the sphere. So remember, isotropic scattering means equally likely to go into any solid angle, not equally likely to have any angle. So when I redo the run, 10,000 points where I draw a psi from this distribution. Now you look at that, there's no collecting of points near the North Pole. They really are randomly distributed in solid angle. So you often get these strange looking results for how to generate angles, distances, whatever it happens to be. And of course, if I had picked a different volume scattering function here, I would have gotten some totally different weird distribution of angles. And if you look on the web book, there's a little table that says, you know, isotropic is this and some other phase function is that, you know, here's the equation to use. Okay, so now we're going to start doing a simulation. So kind of remember what nature does is she draws a random number, she sends a photon out, the photon scatters, the photon gets absorbed, et cetera. So sooner or later, maybe some of these photons reach your detector and you build up the solution. Now remember, there's this albedo of single scattering, scattering coefficient over beam attenuation. And that's sometimes called the probability of photon survival. So what nature does is she draws a random number, she plugs into the equation, she gets the distance the photon goes. Then she draws another random number, compares it with omega naught, and if R is greater than omega naught, the photon is absorbed. So she throws that one away and starts a new photon. If R is less than omega naught, the ray is scattered, so then she computes the scattering angle. So keep in mind here, if omega naught is 1, that says B is equal to C, absorption is 0. And so if R is greater than or equal to 1, am I saying this right? If R, yeah, right. If omega naught is 1, R cannot be greater than 1, so the ray is absorbed. If R is less than 1, in the case of omega being 1, then the ray is scattered. That's telling you there's no absorption. Okay, so Mother Nature will start out, some of the photons get absorbed, some of them might get scattered a couple of times, and now and then one of them reaches your detector. Okay, so nature can afford to waste photons like that. You really can't in your computer. Remember, Mother Nature's putting like 10 to the 21st photons onto a square meter of ocean surface every second. So who cares if like only 1 in 10 to the 17th makes it to your detector? Okay, so there's a lot of ways that you can get around this. And one of them is to think of, well, I'm not just shooting one photon out, I've got a little bundle of them or a packet of them. And so you'll start this photon out with a weight of 1, and then every time it scatters, you multiply the weight by omega naught. So what's that saying is that there's a fraction omega naught of my energy or my number of photons will survive the scattering. And so you do weight of 1 to start. After 1 scattering, the weight is omega naught. After 2 scatterings, it's omega naught squared. 3 scatterings, omega naught cubed. And then you don't end up throwing any of those photons away. You're simply decreasing you're decreasing how much they count towards the final answer. Now, of course, you may still have some of them scatter off and never reach your detector, but at least you haven't thrown any away. Then what you'll do is one like this keeps getting multiplied by omega naughts. So if omega naught is 0.7, by the time it's scattered 10 times, it's got a weight of say 0.7 to the 10th. So that gets to be some small number. And then you finally just quit tracing it when it has a negligible amount of energy left. Okay, here's just some ray paths. As you know, I've got a detector down here at 0, 0, and it's shooting rays off in this direction, and they scatter off in all these different directions. And that's just to give you a visual impression of what light rays would look like if you shined a flashlight in the water, for example. Here's the ones that have only gone through 1 scattering. So they all started out the same direction, and then they go a little distance and they scatter. And here's just the singly scattered ones. Here's the ones that are scattered until omega naught was, or until the weight was less than some value. Okay, let's look at some statistics here. So one of the things you get from Monte Carlo is some idea of how individual light rays are behaving in nature. Just like, you know, you don't see anything like that, or you can't get anything like that out of hydrolyte. You just get the final radiance distribution. Here, you can kind of look at this and say, oh, you know, after 1 scattering, I got a lot of photons that make it like 4 or 5 meters here. And here, after multiple, you know, I'm getting photons out to 20 meters or more. It just kind of gives you some intuition. The other thing you don't get out of hydrolyte is any kind of error bars on your radiances or irradiances. It's simply saying, for your inputs, this is the answer. And there's no statistical noise in hydrolyte. So with Monte Carlo, though, you can build up some intuition about how many rays you need to trace to get a certain level of accuracy in your answer. So here's a little target here. We're shooting photons towards the center of the target. They bounce around. And here's the plane of the target. So this circle might be this target here. In this drawing here, the circle is an angle of 30 degrees off axis at some distance away from, the distance was 10, and I sent out 10,000 photons, and 799 of the 10,000 I started actually made it a distance of 10 and hit the plane here. And within this little drawing is actually 788 of the 799. So you kind of see this sprinkling of points. Most of them just kept scattering almost straight ahead, and they ended up near the middle of the thing. Now and then you get some that scatter off in bigger distances and they hit everywhere else. And of course, a lot of these died along the way. Some of them were backscattered and were never recorded. And if you look at the optical distance here, this was 10 optical distances. Well, if we look at the distance of this plane here, or the instrument from my light source, well, if it's a distance 10 away, then all of the photons here have gone at least 10 optical depths to get there. And some of them have gone 11 or 12 or 17. So I can kind of see a little statistical distribution of how far a photon actually traveled to get from me to the detector over there, 10 optical distances away. And you'll notice some of these guys went 11 or 12 because they're scattering around. So you're getting, this is all kind of going back to the scattering correction in the filter path. The light doesn't go straight through, it bounces around and finally gets out the other side of the filter path. And here's actually a distribution of, in this case, rays going through water. How many times is a ray scattered in getting from here to over there? Well, very rarely, it just goes straight through with no interactions. Typically, it gets scattered about 6 or 7 or 8 or 9 times before it gets over there. And very rarely, it might be scattered 19 times before it finally gets over there. So you can get some intuition about how light rays are behaving in nature from Monte Carlo that you don't get from Hydrolyte. Okay, another thing to look at is statistical noise now. We're going to be drawing these random number generators. And here's a set of runs where I traced 10,000 photons in each run. So I got my answer, which I plotted here as the fraction of the total power that was detected. I think I said that here. So I did 10,000 photons and I computed what fraction of the emitted power made it through. Then I did another run, another 10,000 photons. What fraction made it through? Did another run, another 10,000 photons. And I got this distribution of points here, fraction of emitted power detected. So you can see it's somewhere like 1%, 1.2% of the power that was shot out actually made it to my detector at whatever distance it was here. And so that's what you get. Well, that's 10 runs. So there's 10 different bins here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now I did 100 runs. I got this distribution. I did 1,000 runs. I got this one. I did 10,000 runs, each one with 10,000 photons. I got this distribution. Notice it's approaching what looks like a Gaussian. And there's a little thing called the central limit theorem. You can think of this as being the error or the spread of values. So somewhere here, there's like an average value, and then there's a spread about that, which is the statistical noise in it. Well, the central limit theorem says no matter what the distribution is, that the deviation from that distribution will approach a Gaussian. Amazing theorem. So my light's attenuating exponentially with depth, but the deviation from what fraction of the power got through is still Gaussian, even though that distance travel was this exponential thing. And so you could think of like in Brunswick, there's water usage. Then how much water do people use in their house every day? Somebody's using 10 gallons, somebody 20 gallons, somebody's using 100 gallons, and there's some distribution of how much water is used, and that's not Gaussian, or probably not. But if you look at the deviation, if the city wants to know on average how much water do people use and what's the average about that, it's that deviation that becomes Gaussian, even though the underlying distribution of water usage is not Gaussian. Okay, so people always talk about the law of averages. There's no such thing as the law of averages in statistics, but the closest thing to it is the central limit theorem. Okay, suppose I look at this and say, well, I've done 10,000 runs with 10,000 rays each, and I've got this distribution of values. So yeah, the average is somewhere around maybe 0.0105 or something, but there's a pretty big spread of values here. It could be like 008 to 012. And I need to be more certain if I just do one simulation that I'm going to be within, let's say, 5% of the correct value, not within, 10 or 20% of the value. Then what do? Doing more runs is not helping me. I'm just getting a better looking Gaussian. If I want to make this Gaussian narrower so that I'm more certain of the value, I have to trace more photons or more rays in each run. So I do that. Now I'm tracing 100,000 rays, not 10,000. And here I did 10 runs, 100, 1,000, 10,000. But this is 10,000 runs of 100,000 photons each. And now there's my Gaussian again, but it's skinnier. So I'm more certain if I just did one run and I do 100,000 photons in that one run, I'll get something in here that's maybe good to within 10%. Whereas if I had traced just 1,000 run or just 10,000 rays, I would get some value here, but maybe plus or minus 25%. So there's another little fancy theorem that says the variance in computed values is proportional to the number of rays detected. And remember, it's only the rays that get through to your detector that matter. It doesn't matter if you start 10 million rays. If you only collect 10 of them, it's the 10 is there. So it's only the rays that you detect that count. And of course, the standard deviation is 1 over the square root of the variance. So if I look at this and I say this error is too big, I need to cut this error down by a factor of 10. Then I don't trace 10 times as many rays. I have to trace 100 times as many. So the square root of 100 is 10, and then the sigma will be 1/10 as big. So Monte Carlo gets very expensive computationally when you want to get very accurate results. Okay, enough said there. You now know how to do the Monte Carlo lab and the basic Monte Carlo process. And this is widely used in every field of science, economics, medical stuff, you name it. Everybody uses Monte Carlo simulations. You first have to figure out what nature does. Then you figure out, what these PDFs are for whatever your problem is. And then you try to figure out how can I redo the calculations to maximize the number of rays that I detect. That's the important thing. And so you maybe solve a different problem that was the same as the original problem, or it's different than what you do in the calculation is different than what nature does, but it gives you the same answer. And that leads to this thing called variance reduction. And your goal is always to never waste a ray. That is, don't trace a ray that doesn't make it to your detector. You never achieve that, but that's the goal. So that leads to one of the variance reduction techniques is called backward Monte Carlo. So here's the sea surface, here's the bottom, here's my sensor, it's looking down at the bottom. So here comes some sunlight, it gets through the sea surface, it bounces off the bottom, it goes off in this direction. It did not go into my detector, so that was a wasted calculation. Now, the great minds thought about this and said, well, there's this thing called the principle of electromagnetic reciprocity, which is otherwise known as the I see you, if I see you, you see me theorem. So if I shoot a light ray off in this distance and it bounces all around and off the walls and everything else, and it eventually ends up going over there, if I shoot a light ray from over there in the opposite direction, it will follow exactly the path back and go into my light source. Okay, so what that means is instead of tracing rays from the sun and eventually into my detector, let's send light rays out of the detector and let them bounce around, and some of those will eventually go back to the sky. And every time I shoot a ray out of my detector and it ends up going to the sky, that contributes to my solution because it's detected. Whereas this ray coming in doesn't contribute to the solution. It's wasted calculation. So what you do then, here's what I just said. So I have, let's say, a plane irradiance sensor down here, and it's collecting all this light from the sky, but most of the light from the sky misses the sensor. Now, this has a cosine response if it's an ED sensor. So what I want to do is shoot light rays out of this and let them bounce around and go back to the sky. Now, when I go from the sky to the sensor, I start out with some radiance here, and maybe 1% of that radiance makes it to the detector. When I shoot it the other way, I start this out with a weight of 1, and by the time it gets up here, the weight's down to 1%. 1% of the sky made it down here, 1% of the weight made it up here. Then I multiply that 1% weight by the sky radiance in that particular direction, and that's the value of the sky radiance that would have gotten down to my detector. So it's a very clever thing as to how this backward Monte Carlo works. Now, you still may have some rays that bounce around and they go off down to the bottom of the ocean, and they're never seen again. But most of the time, if you're shooting rays upward, sooner or later, they'll make it up to the sky. And so you've done a lot more efficient calculation, a more efficient use of your computer time. And this is commonly used, like here's from a paper by Xiaoling Shang and Zhangping Li and various people. They wanted to compute the scattering correction for this instrument here, which you see in gray. And one of the things on the instrument, did you have one of those drop packages in this class? I don't think you did. Anyway, so they're calling it a manual version of this thing is stuck on a ship in Boston or something. But anyway, this has an LU sensor here that is going to be below the sea surface. But the sun's up here, there's going to be a shading effect of this sensor looking into the water and looking through the shadow. So they want to figure out how big that effect is. So they literally build in the geometry of this instrument and then do a backward Monte Carlo simulation where they shoot light out of the instrument that's measuring LU. Some of that bounces around, gets to the sky. Some of it might come over here, bounce off the instrument. And they did this, it took a supercomputer to do it, but they did the calculations. And what they found, for example, was first they compared their backward Monte Carlo code with Hydrolyte without the instrument present. And so it's a 1D geometry then. They got agreement to within 1%. So they pretty sure their Monte Carlo code is working correctly. Then there was a paper by Gordon and Ding where they computed the shading correction for a simple cylindrical instrument. And Gordon and Ding found that what matters is the radius of the instrument times the absorption coefficient of the water. And then you got this curve. And so if this product was 0.01, well, there's like a 5% error. If it's 0.1, there's a 40% error, and so on. So then they reproduced the Gordon and Ding papers for a cylindrical instrument, and they got good agreement. The little stars are their study, and the lines here are the Gordon and Ding paper. Okay, so once again, they've now convinced the reader that our Monte Carlo code gives correct answers. There's no factors of 2 or anything wrong. Then they plug in their geometry, put it on a supercomputer, and compute the shading correction for their instrument as a function of sun angle, water IOPs, and so on. Okay.
Hey, Kurt,
Yeah.
you might have said this, but does the backward Monte Carlo assume isotropic scatter?
No, it's whatever phase function you use. The technique of backward Monte Carlo means instead of recording light in a sensor, you shoot light out of the sensor. In either case, it's whatever phase function you have.
The other beauty of this technique is that you can then apply it to different sky conditions. You do computation once, and you can apply it to any sky condition you have. Suppose if you start with a specific sky condition, and you have to do a different one.
Yeah, you'll see that this afternoon. So if we back up a notch, what's going on here is here, what you're doing when you shoot these rays out of here is you're figuring out what fraction of the light will go into this little window, what fraction into this one, what fraction into each of these other sky quads. And then you can come along, you do that calculation. And then you come along and say, now if the sun was here, and I had this sky radiance distribution, I used that fraction of each of these directions to compute how much sky radiance gets down here from all the different directions. And then you move the sun somewhere else. And you'll see when we run the Monte Carlo code this afternoon, you don't actually put in sun angle. It's going to give you for each of the possible sky directions, how much, what fraction of energy got from your detector to that direction and that direction. And then at the very last, it puts the sun in each of these quads, moves around and generates a big table of output. So you can look and say for any sun angle, here's what I would have detected. Okay, so to sum it all up, Monte Carlo technique, it's very powerful, but it can be very inefficient computationally. And it's a brute force technique. And if you want to compute ED, you might not have to trace too many photons. If you want to compute LU, you're shooting all the photons downward. Not many of those get backscattered and go back upward. So you have to trace a lot more photons. And all of a sudden, you've gone from like a 10-minute run to a 10-day run. And that's just the way it works. It's not well suited for some kinds of problems. So if you have like a little point source here, a point detector there, you know, you just, it doesn't matter what I'm shooting the rays out of the source and collecting a point detector, or I'm shooting it out of a point detector and collecting it at the point source. It's 2 points, and there's just no getting around the fact that that's a bad problem. Okay, they don't give you any insight into the beauties of radiative transfer theory, but that's fine, you get the answer. And if I remember when I worked for this guy, Rudy Preisendorf, and we were starting to develop Hydrolyte, the mathematics is just horrible. It's like 30,000 lines of equations inside Hydrolyte. And I said, well, why don't we just use Monte Carlo techniques? And he says, because you learn nothing from Monte Carlo techniques. I didn't quite get what he meant. Now I understand. You don't get this sort of deep understanding of radiative transfer theory, but on the other hand, you can get error bars. Okay, so a few years ago, my wife used to lead a Sierra Club trip through Western China, where they would start in Xi'an, which is already kind of Western China, and then they go all the way over to the stands, Kyrgyzstan, Uzbekistan, Kazakhstan, Pakistan, et cetera, and end up over there. So one day I went along with her one trip, and we saddled up our camels and we headed off into the Taklamakan Desert. And you don't normally think of China looking like that, but Western China is incredibly beautiful country. It's very sparsely populated. The geology is as good as southern Utah. And there's the Gobi Desert, the Taklamakan Desert, some others. And the biggest surprise for me was the artwork, because this is the old Silk Road. It goes back to the Roman Empire and all the way up through Marco Polo in the sort of 1500s. So for, 1500 years, merchants were traveling back and forth between China and Europe along the Silk Road. And, when you dig up a tomb in Beijing, a lot of times, or somewhere in Eastern China, it'll have Roman glasswork in it. And I remember I was in a museum in Italy one time, and they had these old tombstones. And there was a tombstone that said, what's his name? And it called him, I think it was Zaiden Negociant, a silk negotiator or silk merchant. So this guy was a Roman whose business was trading silks with China. And Marco Polo, of course, went to China to, his uncle and everybody they were merchants. Well, anyway, they're all coming along this area, and there's just amazing artworks. Now, this is actually, there's a type of pottery. It's called Tang Cai Sa, which means a Tang San Sa, Tang San Sai, which means Tang 3-color. And you always get this cream color, kind of amber and green glaze on this the ceramic stuff. And these can be this high, they can be life size. They're just amazingly beautiful pieces of sculpture or pottery that have been dug up out of all these tombs and stuff. So here's just the head of a horse I photographed. Here's some dudes riding on the back of a camel. Musicians are playing all kinds of musical instruments. So this is like the Tang Dynasty equivalent of a, party limo. And so it's going to be a good time in town tonight, but beautiful pottery, just incredible. There's a lot of it extremely detailed. And here's the Tang Dynasty was basically 600s through 900s. And it's a whole different lecture, but the Tang Dynasty poets of Du Fu and Li Bai are probably the best poets I've ever read. Just amazing poetry. Here's a wine jug. This is in the museum in Xi'an. This little guy is about this long and this high, and it's an ox thing. He's got a little tiger on his back. You open up the tiger, you pour the wine in, you put the lid back on, and then you pour the wine out of the ox's nose. So, I mean, that's, just what you want to see if you were entertaining at Mar-a-Lago, for example, has come out, pour everybody's wine out of an ox nose. But an amazing piece of bronze. This is 1000 to 900 BC in the Zhou dynasty. That's like the second of the Chinese dynasties. We're out wandering around in the middle of the Gobi Desert near a place called Jiayuguan. And the Gobi Desert, there's like no buildings there. But every once in a while, there's basically a hole in the ground, and you go like 30 feet underground, and they've hollowed out these big tombs underground. And so these tombs the walls are lined with bricks. And so this is a photograph of 4 of the bricks on these tombs that are 30 feet under the Gobi Desert surface. And it's just astoundingly beautiful. They're like this big. Here's some guys playing music. Here's a guy hunting antelopes. Here's some guys cooking dinner. Here's some guys plowing a field. And I never heard of this stuff. We go there, you just drive up. It's like driving up in the middle of a dirt parking lot. You get out, there's this like little hut thing. You go on the hut thing. Here's a staircase going down underground for 30 feet, and the walls are, you get down there, there's all these tombs, it's just, it's incredible. So this is from what's called the Wei Jin era, which was after the fall of the Han Dynasty around 200. Beautiful art. Here's, I guess this is an ibex or something, solid gold little thing. It's about this high, just amazing. Here's a teapot thing where there's no lid on it. It's one of these trick deals where there's a hole in the bottom. And so there's a little like funnel thing inside. So to fill the teapot, you turn it upside down, you pour the tea in the bottom, then you turn it back right side up, and then you pour the tea out of the dragon's mouth. I mean, it's an astounding piece of pottery. In a place called the Mogao Caves, which is near Dunhuan. When you get home, Google Mogao Caves. It's amazing. So there's almost 500 caves in a big cliff. It was a stopping spot on the Silk Road. You'd stop there maybe for a month, let your camels fatten up again, and catch up on gossip with everybody. And if you're a wealthy merchant, and of course, this was all Buddhist at the time, you're a wealthy merchant, you will fund digging a little grotto in this rock cliff and having it painted with all kinds of Buddhist art. And the richer you were, the bigger the grotto that you could fund, and the better the artwork, the better favor you were going to be in when you died and went to your reward. So, as I say, there's almost 400 of these. This is just not my photo because they don't allow photos there. So the flashes don't destroy everything. But this is what you see. You can walk along. They built these kind of walkways out in front of the caves. You can kind of look in. You'll have these caves with carvings, and the walls will be painted with just the most astoundingly beautiful art you've ever seen in your life. It's very well preserved. It was not destroyed by the Red Guards during the Cultural Revolution. Zhou Enlai spread the word, don't mess with the Mogao caves. And so the Red Guards stayed away. So it's all very well preserved. And now this is like a major tourist draw. It's not really on the main tourist thing where everybody goes to Shanghai and Beijing and Xi'an to see the terracotta warriors, but it's really, really worth the trip. And here's, just a typical painting off of a wall of, once you get into all your Buddhist stuff, it all makes sense about what's going on here. Absolutely astounding. And you go there, you spend the whole day at the Mogao caves, and you see maybe 20 of them because you're just standing there for like 30 minutes looking at this one, and then you go to the next one. And then there's still another 450 to do. Highly recommend it. This is the best piece of sculpture I've ever seen in the whole world. And I've seen Michelangelo's stuff in Italy and all of that. But it's called the Flying Horse of Gansu Province. It's about this high, it's bronze sculpture. And the Chinese characters read horse tread, fly swallow. A horse treading on a flying swallow. So right here, you can't tell it in my photo, but this is actually a little bird, the swallow, flying, and the horse's hoof is resting on the back of the swallow as the swallow flies, and it's so perfectly balanced, it's just incredible. This was dug out of a Han Dynasty general's tomb, and it's considered like one of the greatest Chinese national treasures, but it's just so perfectly made and perfectly balanced. I don't buy many souvenirs when I go to places, but I have one of these on top of my china cabinet.
I have one of those.
Beg your pardon?
I have a replica of one of those too.
Oh, yeah. The real one's about this high. Just incredible piece of art. So anyway, there's more to China than just, seeing the Forbidden Palace in Beijing. The art there is incredible. And all the Chinese provinces have amazing provincial museums that some of them are just almost equal to the Smithsonian. They're really, really good. So this was in the Gansu Provincial Museum in Lanzhou, which has been called the world's most polluted city, but it's still got a great museum. So that's it. So 11:30, you start up again at 1 o'clock. We'll do the Monte Carlo lab, and then somewhere drag that directory over to the computer and away we'll go. Hopefully. Oh, yeah.